So let's speak a little bit about how hard is it to compute a Nash equilibrium in a normal form game. This is an involved topic, and I'll just give you a taste for it. Let me draw your attention to two specific algorithms for computing a sample Nash equilibrium in a game. These are two out of a long line of algorithms that have been investigated, and these are sort of two extreme. The one of them starts with a mathematical formulation of the problem called a linear complementarity problem. And once you set it up as a mathematical optimization problem, you can apply various algorithms to that. And the most famous one for two players games is due to Lemke and Hausen. And this is an algorithm that really displays a deep understanding of the mathematical structure of what a game is and the nature of Nash equilibria. On perhaps the other extreme is what is called the support enumeration method, a recent procedure that doesn't have as deep an insight into the structure of the problem. It says simply the following. It says, if you fix the support of the strategies of the player, and the support of the strategy players are those actions that are played with non-zero probability, if you fix that support, then the problem becomes very easy. You can set it up as a linear program and solve it efficiently. And that would be the end of it if it weren't for the case that indeed there are an exponential number of supports to explore. And so the trick in this procedure is to explore them cleverly using clever heuristics. And that's called the support enumeration. There's a clever heuristic for how to enumerate those supports and check them one by one. Although the latter procedure is not as smart or as insightful as the Lemke-Hausen, it turns out that in practice it tends to run very fast. So we've seen the algorithm. People have tried very hard to find algorithms computing a sample Nash equilibrium. And it does seem hard. The question is, can we somehow capture that formally within the complexity hierarchy? And for that, we need to introduce some new concepts. The essential concept is that of the new class of problems called PPAD, for polynomial parity arguments on directed graphs, introduced by Christos Papadimitriou in 1994. We won't go into detail, but just so you know the chronology, PPAD is a specialization of a class called TFNP, which is in turn was a specialization of a problem called FNP. Going in detail here is beyond the scope of what we want to speak about, but it does help us now position the complexity of finding a sample Nash equilibrium in the complexity hierarchy. And again, we have the class of polynomial time problems, of problems that can be verified in polynomial time, with these being the hardest among them. And given that, PPAD turns out to reside somewhere within this class. Now again, we don't know whether this entire class does not collapse and all become one and the same. It's widely believed that it does not, but proof doesn't exist. However, we do know that PPAD lies someplace in between P and NP. Now, what does that have to do with the problem of computing a Nash equilibrium? Well, that's where the following theorems come in. Originally, it was shown that the problem of computing a Nash equilibrium is complete for this class PPAD. That is, it's the hardest among all problems in that class. Initially proved for 4 players, then for all 4 games with 3 or more players, and then finally in 2006 for all classes of games. And so we widely believe that the problem is not polynomial, cannot prove it, but we do know where it resides within the complexity hierarchy that we are familiar with.
Hi folks, this is Matt Jackson again, and so now let's take a look at mixed strategy Nash equilibrium in practice and try and understand a little bit about what it can tell us about what we should expect to see. So let's start with the situation of soccer penalty kicks, and this is a quite natural application of mixed strategy equilibria because they're ubiquitous in sports and competitive games, so situations where it actually pays to be unpredictable. So by not knowing what the opposition is going to do, it makes it a little more difficult for you to pick an optimal strategy in these games where one player wins and the other player loses. In particular, in soccer penalty kicks, we're looking at a situation where a kicker has to try and kick the ball into the goal. The goalie can try and move to deflect the ball. And this happens very quickly, so it's essentially a simultaneous move game. The kicker is choosing to go either in their simplified version, say to the right or the left. The goalie is then going to dive to one side or the other side and try to deflect the ball. And if the goalie guesses correctly and ends up in the same direction as the kicker, then they have a higher chance of saving it. If they go in an opposite direction, they have a lower chance of saving it. Okay, so how are equilibria going to adjust to the skills of the players? So let's suppose, for instance, as a kicker, that I might be biased. I might be able to kick the ball more accurately in one direction than the other. So if you ask me to kick it towards the left side of the goal, it might be that I hit there very accurately. If you tell me I have to kick it towards the right side of the goal, it could be that I'm less accurate and I have a higher chance of just missing the goal altogether. So how is the equilibrium going to adjust when we change one of the players' adjustments in terms of their skills? So let's have a peek at this. Should a kicker who kicks penalty kicks worse to the right than the left kick more often to the left than the right? So if I'm worse on kicking towards the right, does that mean I should kick in the opposite direction more often? Well, let's have a peek. So let's start with just the simple version, just to get our ideas fixed. So imagine that the setting is one where the kicker and the goalie, so let's have the kicker on this side. So the kicker is the row player, the goalie is the column player, and if they end up kicking, if the kicker goes left and the goalie also happens to go to the left, then the goalie saves, and the goalie gets a payoff of 1, the kicker gets a payoff of 0. If instead we're in a situation where, say, the kicker goes left and the goalie goes right, then the kicker scores and gets a payoff of 1, and so forth. Okay, so this is just a simple variation on matching pennies, and in this situation, what's the equilibrium going to be? The equilibrium is going to be quite simple. It's just going to be that the kicker randomizes equally between left and right, the goalie randomizes between left and right. Each person has a probability half to win from kicking to the left or right, going left or right. So it's a very simple game, and we have a good idea of how to solve that one. Okay, so now what are we going to do? Let's change things. And now we've got a kicker who sometimes misses when they go to the right. So in particular, if the goalie happens to go to the left and the goal's wide open to the right, the kicker scores 75% of the time, but actually misses completely 25% of the time. Okay, so this is a kicker who still does well if they go left and the goalie goes to the opposite direction, but now they have a lower probability of winning when they're kicking right and they have a wide open goal. Okay, so how should this adjust? What should the new equilibrium look like? So let's suppose, let's first of all try and keep the kicker indifferent. So let's think of the goalie going left with probability P, right with probability 1 minus P. For the kicker to be indifferent, what has to be true? Well, what's their payoff if they go left? Their payoff to going left is just 1 times 1 minus P. Their payoff to going right is 0.75 times P. These two things have to be equal in order to have the kicker be indifferent. So what do we end up with? We end up with 0.75 p is equal to 1 minus p. So we end up with 1 equals 1.75 p, or p is equal to 1 over 1.75, which is equal to 4 over 7. Okay, so that tells us that the goalie should be going left with probability 4/7 and right with probability 3/7. Okay, so we know what the goalie is supposed to be doing. So now the fact that we changed, the goalie's payoffs haven't changed, but the fact that we changed the kicker's payoffs meant that the goalie actually had to adjust, right? So even though the goalie's payoffs haven't changed at all in this game, the new equilibrium has a different set of probabilities for the goalie in order to keep the kicker indifferent now. Okay, so now let's see what the kicker is going to do. So how are we going to see what? So let's suppose that the kicker goes left with probability q, right with probability 1 minus q, and let's solve for q. Well, for the goalie to be indifferent, what is their payoff if they go left? If they're going left, they're getting a q probability that they match, so they get q plus 0.25 times 1 minus q if they go left. If they go right, instead, what are they getting? They're just getting 1 minus q, right? So these two things have to be equal. So we end up with q is equal to 0.75 times 1 minus q. So q over 1 minus q is equal to 0.75. What does this tell us about q? That tells us that q is equal to 3/7. Okay, so what's going to happen when we work out this, we get 3/7 for the probability that the kicker is going to go left and 4/7 for the probability that the kicker is going to go right. So overall, what do we have now? We have the strategies looking like this as we made this adjustment. And we noticed two sort of interesting things about this. One is that the goalie's payoffs didn't change, but they still had to adjust their strategies. And the second is that the kicker is actually kicking more often to the weaker side, right? So their right foot got worse than it was before, and they're actually going in that direction more often. And why is that? It's because the kicker, the goalie, has also made an adjustment in this game. And so the comparative statics in mixed strategy Nash equilibria are actually quite subtle and somewhat counterintuitive in terms of what you might expect. You get a bias so that this becomes a weaker direction, and the equilibrium adjusts so that the player goes in that direction more often. So let's have a look just through the intuition here. Again, the goalie strategy must have the kicker indifferent. And so when we went through those payoffs, the goalie goes left more often than right. And the kicker actually, so sorry, there's a typo here. The kicker actually goes right more frequently, right? Goes right with probability now 4/7. So they've increased their probability on that. And when we end up, what we see is the goalie strategy is adjusting, but we also see that the kicker adjusts to kicking more towards their weak side. So the goalie now actually has a slight advantage. So if you go through and calculate the probability that the goalie is going to win, they're going to win 4/7 of the time in this match. And we can think, what would happen if the goalie actually just stayed with their old strategy of still going 50-50? Then the kicker could always go left and win half the time instead of 3/7. So the fact that the goalie has to make an adjustment is because they have to defend more to the left side to defer, because now the kickers has a better chance of winning on that side. So the goalie goes more in that direction. That pushes the kicker towards their weaker side in order to make sure that the goalie is willing to go to the left side with a higher frequency. So by adjusting the strategy to keep the kicker indifferent, the goalie actually gets advantage of the kicker's weak right kick and wins more often. Okay, so just in terms of summary and mixed strategy and soccer penalty kicks in general, players must be indifferent between the things that they're randomizing over. That produces very interesting and subtle comparative statics. And, there's a question that might come up in your mind. Do people really do this? I mean, this is fairly complicated, right? So, 50-50 we can figure out. Once we get these games where a player has an advantage one way or another, then the actual mixture becomes fairly complicated. And it's not so obvious that players will actually do that. So we'll take a look at that and see if this actually bears out in practice. Okay, hi folks. Let's take a look at some data now on mixed strategies and begin to see whether or not some of the subtleties that we were talking about earlier actually play themselves out in real incarnations of these games. So in particular, we mentioned that mixed strategy Nash equilibria can have some counterintuitive features, and they're can be somewhat subtle to solve for. So we might wonder whether people actually really obey the predictions of Nash equilibrium in these settings. So let's have a look at professional soccer penalty kicks. And we'll look at some data that was gathered by Ignacio Palacios Huerta in 2003, where what he did was he actually looked at a whole series of FIFA games that he recorded off of television, different shows. He looked at 1,417 penalty kicks in the Spanish league, England, and Italy, and so forth. And so he's looking at high-level soccer and looked at penalty kicks. And what he did is he kept track of whether people kicked to the left, they kicked to the center, they kicked to the right, and whether they were using their left leg or their right leg. And we're going to look just at the simplified version that corresponds to what we analyzed earlier, which is just a left kick, right kick, and the goalie can either move left or right, which he actually analyzes a subset of the data on page 402, and we'll look at what data he actually has from that paper. Okay, so here's, based on what he finds out of these 1,417 penalty kicks, these are sort of the averages. So in situations where kickers go left and goalies go left, kickers win 58% of the time, goalies win 42% of the time. In situations where the kicker goes left and the goalie goes right, then the kicker wins 95% of the time. If the kicker goes right and the goalie goes left, the kicker wins 93% of the time, and so forth. So these are the actual numbers that Ignacio finds based on these recorded penalty kicks from the 1,417 games. Okay, so we do see that there's biases here. There's some advantages and disadvantages. So going left against right is slightly better for a kicker than going right versus left. Not so different, but left compared to right, we see a little bit more of a difference. So this is an asymmetric game. It's a fairly subtle one. So we have to see whether or not we're going to end up with the Nash equilibrium in this game. Okay, so why don't we do the following? Given those numbers, we can pause the video and solve the game. So you can take a look at this, try and figure out what the probabilities that the goalie should go left. So say the goalie is going to go left with probability PG, the kicker is going to go left with probability P sub K, solve for P sub G and P sub K with this matrix. So you're going to put PG here, 1 minus PG here, PK here, 1 minus PK here, and try and solve for the mixed strategy Nash equilibrium of this game. So take a few minutes, pause the video, try and solve that, and then we'll come back and look at what the solution looks like. Okay, so you've had a chance to look through that. Now let's see what actually is happening in this game. So what we need PG to make the kicker indifferent, right? So if the kicker kicks left, we can figure out what payoff they get. If the kicker goes right, we can figure out what payoff they get. So in particular, the goalie's probability of going left versus right must have the kicker indifferent. So when we look at the kicker's payoff from going left compared to their payoff to going right, has to be the same. You solve that out, and what do you end up with? PG is roughly 5/12 in this case, or 0.42. So if we do the same for the kicker going left versus the kicker going right, you can go through that, and setting the goalie's payoff from going left versus right being indifferent, what do we end up with? We end up with PK, the probability that the kicker goes left is 0.38. So in terms of what we found that goalies should go left 42% of the time. That leaves them going right 58% of the time. Kickers should go left with probability 0.38, which then puts them going right with probability 0.62. So we have a simple prediction based on the actual frequencies with which kickers and goalies score when they go left versus left, right, and so forth. So if they were doing this facing populations of people going left and right, and these are the payoffs, then this is how they should be behaving. Okay, so what happens in the data? Let's take a peek. So the Nash frequencies, goalie going left, 42% of the time, goalie should go right, 58% of the time. Kicker should go left 38% of the time. Kicker should go right 62% of the time. What do they actually do out of 1,417 games that were recorded? So we have a non-trivial amount of data here. Goalies, 42-58, right on the money. Kickers, 40-60, so very, very close to the 38-62. So in fact, when we see professional soccer players playing and we look at the payoffs they're getting, they're playing almost exactly the Nash equilibrium in terms of the mixed strategy. Or in this case, given this is a zero-sum game, this is the same as the max-min strategies. And if we ask a question of exactly how they learn to do this, it's not necessarily true that they're sitting down and looking at a matrix and calculating these things directly. But over time, they get it. They should be indifferent between going left and right. So if the other players are going in one direction or the other too often, and they start they can get a better payoff from going one direction or the other. They'll take advantage of that, and so things have to adjust in keeping them indifferent over time. So, do players randomize well over time? Yeah, pretty well. Ignacio's paper goes in much more detail on this and looks at things like how well they do in terms of mixing. If you wanted to mix 50-50, one way to do it would be to go left one time, then right the next time, then right, left the next time, and so forth, and just alternate. That's obviously not randomizing. And so instead, there's a question of whether people randomize so that they're really unpredictable over time. And Ignacio finds that they do fairly well, even in terms of the strings of kicks that they have. There's other questions you could ask. How well do they perform under pressure? If it's a big game and it's a very important kick, do they tend to go towards their stronger foot? Do they become predictable? In fact, now you see more and more professional sports teams hiring statisticians, hiring game theorists, keeping track of exactly what's going on in terms of other teams' tendencies. What do they tend to do in this situation? What do they tend to do in that situation? What's our best strategy in response to that? So, going through and analyzing these things has become more of a trend. In other sports, there's similar analyses. There's a very nice paper by Mark Walker and John Wooters, the American Economic Review, looking at tennis and serves. So, which side you have to serve into a given area. Do you serve towards the left side of it, the right side of it, the center? How does it depend on whether you're right-handed, left-handed, which directions you're going in, and so forth? So they analyze a series of professional tennis games, and similarly, they find that minimax play is a fairly good predictor of exactly what's going on. And there's also questions of how well people really mix over time, but the equilibrium predictions do fairly well. Okay, we see there are going to be games that have mixed strategy equilibria. In particular, zero-sum and competitive games will tend to have them in a lot of situations. Players have to be indifferent between what the players they're facing. That gives you some very interesting comparative statics. We asked the question, do we really see randomization? We found, yes, in professional sports, we do see randomization. There's lots of other things in the world where you see randomization. So predator-prey games, in nature. If you come up upon a squirrel thinks you're trying to catch it. What does it do? It randomizes a bit. So it's very unpredictable to figure out which way the squirrel's going to dart when you're walking by it. It's following essentially a randomized strategy. Many business interactions. So if we look at things like audits, tax auditing, that's a game where you're going to see a situation where it's competitive, and tax authorities don't necessarily want you to know exactly whether you're going to be audited or not. They might want you to have some uncertainty. So they can't audit if they can't audit everybody in the population. If there's a cost to auditing, that's going to be a game where they're going to mix, and that randomization might help tax authorities. So there's a lot of settings where random checks, random audits are essentially optimal strategies as part of some game, and where Nash equilibria, in particular mixed strategy Nash equilibria, will help us understand those things.